Yeah, so I'm going to talk about a method for designing finite element methods for ODEs, such that we can preserve some given Lie symmetries. And this is joint work with Alex Bilo, who's also at Memorial University in Canada, and Francis Valquet, who is at Monmouth in the US. So just to try and keep things simple and try and stay reasonably within the time limit, I'm only going to give the rough outline of how this argument works. So I'm going to be hiding a lot of the complications. So if you're interested, you can come and talk to me about these later. So I'll be around until the middle of August. And also a lot of the tools that we're going to be using, Elizabeth Mansfield has already covered in her talk on Tuesday. So hopefully this should be relatively easy going for you. But again, as Tuesday now was quite a few days ago, I'm going to go through all these details again. It has. I mean, this. Well, I don't know about you, but I have quite a bad memory for some things. So it's good to just cover things again. Okay, so the outline of the talk is going to this talk is going to go roughly as follows. So I'm going to start by introducing what a Lie point symmetry is, introducing what a finite element method is for ODEs. So for some of you, this is going to be very standard. And then I'm going to get on to discussing this methodology for how to design finite element methods which preserve symmetries. And I'm going to do this mainly through looking at a particular example. And then we're going, if I have time, we're going to look at some numerical results. So there should be some pictures at the end. So it'll all be worth it. Right, so we'll start off on a maybe too basic level by introducing what an ODE actually is. So we have time in some interval 0t, and we say that y, which is a function of time, is a solution of an ODE if this function curly f is equal to 0, where this function depends on t, y, and y's derivatives up to some fixed order. And we're also going to restrict ourselves to initial value problems. So we're going to always assume that our ODE is initialized by some values on its solution and the solution's derivatives. Okay, now what is a Lie symmetry for this ODE? So let's say that we have some Lie group G. Then this is a symmetry group of a given ODE if for all elements in this group this identity holds. So this identity is basically telling us that if we take an arbitrary group element and we act on the variables of our ODE with it, then after some kind of simplification, we're going to recover the original ODE. Okay, so that's all there is to. I shouldn't say that, but this is all you need to define a Lie symmetry for an ODE.
Is the action always a prolonged action, or do you allow general actions so that you act completely differently on the derivatives? Or
it's always prolonged.
Always prolonged.
Yeah, so yes, you're ahead of me a little bit here, so I'll tell you that again in a second. So just to keep our notation simple, we're going to write the group action on something just through a superscript hat. And we're also going to only consider what are known as Lie point symmetries. So what this means is that we take our t and y and we map them to other functions of t and y which are parameterized by some group action. And the important exclusion that we're making here is that the group action can't add more derivatives into the problem. Okay, so we can't take y and map it to yt.
Epsilon is now the group operator G?
Epsilon are the parameters of the group action. Yeah. So the group action always depends on some number of parameters, and here I'm just noting to be epsilon. Okay, so let's look at an example, because examples are nice. So we're going to consider the Panevet type equation. where we just have ytt minus ut squared over y is equal to 0, and this is going to be subject to some initial conditions, and of course because we're dividing through by y here, we need to assume that our solution is never equal to 0, which it turns out is quite a reasonable assumption. So if you look at the exact solution, this is just going to be an exponential. Now, we're going to look at a two-parameter Lie symmetry of this equation. So we're going to look at the symmetry which maps t just to itself and y back to y multiplied by some exponential of at plus b, where here a and b are the parameters which define our group action. Now this isn't the only symmetry for this problem, so there's actually a much larger symmetry group that we could consider, but here I'm just going to restrict things to this two-parameter symmetry well, to make this talk a bit clearer and easier to understand, and also because it leads to some quite nice numerical results. Now, to act on our ODE with this group, we have to know how we have to know what it means to apply the group action to derivatives of y, and as Christian alluded to, this is simply done through prolongating the group action, as is explained on Tuesday. So basically, all we do is the group action applied to yt is simply defined through differentiating the group action defined on y. Okay, and we end up with these two expressions. And you can see, for those of you who are quite fast at mental math, maybe some of you can see already that if you substitute all of these expressions back into our ODE, the ODE is preserved. For those of you like me who can't do mental math that quickly, I'm just going to ask you to believe me for now. Okay.
Sorry, so what's the group?
So the group, so it's a Lie group which just it's defined through its action on t and y, and it's just defined to be a mapping which takes.
But in this case, what group do we have here?
Is it R2 because it has two brackets?
Yeah.
It's what?
Yeah. Pardon?
Affine group on the real.
Scaling and
Yeah. Yeah.
So the G in this case is A comma B?
Yeah. It's so G. All of the examples of G can be given by different values of A and B, where A and B are real. Yeah. Okay, are there any more questions before I move on a bit? Good. So now we have to think, so we have this arbitrarily high order ODE, and I'm going to tell you that we want to design a finite element scheme which can handle an ODE of any arbitrary order. So the question becomes, how do we design this finite element scheme of arbitrary order using one single methodology? So does anyone have any ideas? Yep. So what we're going to do is we're going to rewrite our ODE as a first order system. So we only need to discretize first derivatives. So we can rewrite a general ODE as just a first order system. So basically we introduce auxiliary variables for y and its derivatives. So we denote these as u0, u1 up to um, replacing up to the nth derivative in time. And this just gives us the following system of equations, which are now subject to initial data on all of our u's. Okay. So now we have to think a little bit about what the symmetry group for our new system is going to be. So through the prolongation that I have just shown you, you can well define the group symmetry on all of these auxiliary variables. But more than this, actually, because we're now writing we're writing our ODE as a system, we can be introducing additional symmetries. But I'm just going to tell you that we're not going to worry about those too much here. We're just going to focus on the original symmetries of the problem. Yep. Now let's go back to our example, just to clarify what we're doing. So we have our second order equation. If we replace y with u and yt with v, then we can rewrite our second order ODE as the following first order system. And this first order system is invariant under the following group transformation. Okay, so if you compare this to the original group transformation, the first two actions are the same, except for I've replaced y with u. And now we define the group action on v simply through the prolongation of the group action on the original variables y. And essentially the only difference here is that we've replaced all of our yt terms with v. Okay. So are there any questions or comments? Good. Right, and from this point onwards, I'm just going to talk about this example, just to make the exposition notes a bit simpler. But everything that I'm going to talk about can be said in the general setting, but not in half an hour. Okay, so now let's move on to our finite element discretization. So we are dealing with ODEs, so we just have one dimension. So defining finite elements isn't too difficult in this case, so we don't need to use any particularly fancy techniques. So we just partition our interval into n different elements, which we are going to denote as in, and then we can define our finite element space over these elements. Okay, so we're going to define the discontinuous finite element space of some degree q to be the space of piecewise polynomials of degree q over each element, where we're not going to enforce any continuity on the boundaries of the elements, so on the nodes. Through this definition, we can also define the continuous finite element space in exactly the same way, where we're just going to be enforcing global continuity. So for example, in the discontinuous space, in the case where we have discontinuous piecewise constants, we have functions like this blue line here. And in the continuous case, when we're thinking about continuous piecewise linears, we have functions like this red line here. And again, just to clarify, in my notation, I'm referring to continuous finite element functions simply through a superscript capital C. Okay, are there any quick questions about this notation or what it means? Or that's good. So you're all either completely understanding or a little bit shy. So now we've defined the finite element spaces, we can go on to define our method. So this might look a little bit unconventional for some of you in spatial finite elements, but I assure you this is the correct kind of method to be using. So I could talk for quite a while about it, but I'm not going to go into too much detail because of the time restrictions here. But this method was analysed by Estep and French in the mid-90s, and it was I believe it was introduced at some point in the 80s. So it's given by, so we're going to consider it just for our example. So it's given by seeking some discrete functions u and v, which are in a continuous finite element space of degree q plus 1 over a single element, such that the system formulation of the ODE holds when multiplied by a test function and integrated over the element. And here our test functions are in a discontinuous finite element space of 1 degree lower. Okay, and also because of the continuous, so we have a globally continuous trial function, so u and v. So these functions are, so on each element, these are going to be initialized by either the value of their solution on the previous element or by the initial condition. So this is a time stepping method. So we're marching forwards through time. And just as a quick sanity check for you all, I'm going to show you that the degrees of freedom of this finite element method match up in trial and test functions. So let's consider the case where q is 0. So our trial functions are continuous linears. So we have 2 degrees of freedom on an element, and one of these degrees of freedom is fixed by our initial condition. So we're just left with 1 degree of freedom on each element. And our trial functions, our test functions, sorry, will be discontinuous constants. So these only have 1 degree of freedom. So both the trial and test functions both only have 1 degree of freedom. So this method does make sense. Yeah.
So this is actually a Petrov-Galerkin method? Because you have different...
I would call it that as well, but in the literature it's always referred to as the continuous Galerkin method.
Yeah, but you are not doing any variational form because you are not going to integrate by parts. So you are just projecting. I mean, you are just projecting, right, on the discontinuous space.
Yes. Yeah. Notation is always notation and naming convention is always a difficult one for me. Right. So there is one caveat to this method. So for our example, we have this term 1 over u here. So we're dividing through by u, which is our numerical approximation. So we have to assume that our discrete approximation is never equal to 0, which we don't actually know. So this really is an assumption that we have to make. So at this point, if this did happen, our methods in theory could break down numerically. Okay, so what are the discretely symmetries of this finite element scheme? So luckily, within each element, our finite element functions are smooth because of they're just polynomials. So we can define this discrete action simply just through just analogously to the continuous action. So we define it simply through capitalizing all of our notation. Okay, and we can do this just because we're smooth within each element. Okay, so if we apply this group action to our finite element approximation, we end up after a little bit of work with the following. Okay, so you'll notice here that we have these exponential factors. So we have the exponential of at plus b coming in under the integral in both of our equations. Okay.
I have a silly question.
Sure.
I have a silly question. In your finite element algorithm,
Yeah.
What is Vt? Because you have a polynomial in every element, are they depending on time, or I mean, what is your time derivative then?
It's the continuous time derivative because we're using continuous finite element functions.
Yeah, but then, so you mean your polynomials are depending on time?
Yes, yes. So there is no space at all.
Okay.
This is all in time. Okay. So the finite elements are completely in time. There's no space. And time is discrete. Okay. So under our group action, because we have these exponential factors, which in the continuous setting, if we weren't under an integral, we'd just be able to divide these out because we know they're never 0. But here, because they're under an integral, we can't get rid of them. So our finite element method is not invariant under the group action. Okay, so now the question is, what are we going to do? So actually before this, I should probably talk about some complications before I move on to the moving frames part. So here we're considering a relatively simple group action where time is just time is not acted on. Okay, so in general we have to get if we consider a case, if we consider our group action in time to be non-trivial, so for it to do something interesting, we have to think a little bit harder about how to actually apply our group action to a finite element scheme. So the group action is also going to affect the infinitesimal operator, dt. This isn't too difficult to handle. We can do the same thing here as we were doing a continuous setting. It also is going to shift the integral of our domain because of we're local. So this could lead us to run into some problems. But the biggest issue is that if the group action is nonlinear in time, it's going to fundamentally change the nature of our test functions. So here we really have to think a bit harder. And I'm not going to answer this question in this talk. So it's something for you to come and talk to me about afterwards if you're interested in this. So back to how we're going to solve this problem of having designing an invariant finite element method. So we're going to use moving frames, which can be read about in Felton Olver's paper or in Liz's book, and she described quite nicely in her talk on Tuesday. So we can define a moving frame which acts on a vector z, where z is t, u, v, ut, and vt, to be defined to satisfy the following identity. Okay, and this moving frame is itself an element of the transformation group. So it is itself a very particular group element. And after defining this moving frame, we can define the invariantization of a method, which we would hope would lead to an invariant method. Otherwise, our naming convention is incredibly misleading. Okay, so we can define so if we rewrite our whole finite element approximation as just f of z is equal to 0, then we can define the invariantization of this method to simply through defining iota such that we essentially act on our vector z with our moving frame applied to z, and the idea is that this leads to a method which is invariant under the group action. Okay, so we can see this actually through a nice one-line proof. So if we consider the definition of the invariantization and we apply the group action to it, we get to the second line of the calculation, and then if we apply the definition of a moving frame, then we get to the third line of the calculation, and then we notice that we have G inverse composed with G, which is just going to cancel out, and we're going to recover the original invariantization. Okay, so the invariantization is invariant, which is good, and this is the tool that we're going to use. So and this argument is a bit more complicated in the finite element setting, so we have to worry a bit more about some extra details, but I'm going to skip over them here. So the thing that we have left to do is to construct our moving frame. Okay, and so we're going to do this. So was there a question? Okay, so we're going to do this by so first of all we're going to restrict our z's just to make life a bit simpler and avoid some technical complications. So we're going to restrict our z's to just be t, u, and v, and we can construct our moving frame through considering a cross section of this space. So for example, if we're considering so if we fix the cross section where u is equal to the sine of u, so u is equal to positive or negative 1, and v is equal to 0, then our moving frame is defined to be the unique group element which maps this cross section to itself. Okay, so what this means is that through acting on so if we're applying the group action to this cross section, we yield the following two equations, which are known as the normalization equations, and through solving these for the group parameters A and B, we find our moving frame. Okay. Are there any questions on this? Yes. Okay. Then I'll speed up. Okay. So we have our original finite element method. Under the group action, it ends up being this, which is invariant. And if we choose our group element to be the moving frame, then we end up basically dividing through by a factor of u, and the method that we get is indeed invariant. Okay. Now I'll skip over the first example because it's a table of results which take a while to explain. So we'll go to the second, which is the case where we're thinking of modeling exponential growth. So our exact solution is just an exponential, and here we look at the standard scheme in red and the invariant scheme in black. And you'll notice that the error for the standard scheme is increasing over time, but the error of the invariant scheme is not growing. And even more than this, if you look carefully at the nodes, so at every factor of quarter, or every quarter, the error is actually 0. So the invariant finite element scheme is exactly solving the ODE at the nodal points. Okay, and just to conclude, for more details and examples, either talk to me or you can have a look at our preprint on archive. And the methodology I talked about, it can be applied to any Lie point symmetry, including non-projectable actions. And it can be applied to arbitrarily high order finite element approximations. And one of the motivations behind this work is actually to try and get more ideas on how to design symmetry invariant methods for ODEs. So we're hoping this approach informs for PDEs. So we're hoping that this approach can inform new methods for designing invariant methods for study of PDEs. Okay, so thank you for listening.
Thank you very much for the talk. And again, I think that we have time for short question while the next speaker is setting up the computer.
Do we have time for a question?
For one question, when the second.
Yeah, I was going to ask, so the invariantization of this PDE, it looks like you just made it so that the action by G is just multiplication by G inverse. Did you ever use that this was a symmetry of the equation itself? Or did you just add two canceling things?
Sorry, I don't understand. So what?
We can talk about it afterwards then.
Okay, sorry.
Remember that the students actually liked these questions at the end.
Oh, okay, but I know we're in a hurry. So.
All right, so thank you very much again for this talk.